Hello everyone, welcome back to the another session in design and analysis of algorithms. The topic name is topological ordering. This topic you will find in 4th unit as topic number 4. Now let's get started. First of all, we'll see the definition of topological ordering. Then we'll take some example to find the topological ordering of a graph. Now, the definition is a topological ordering of G is a graph is an ordering v1 comma v2 up to vn of the vertices of G such that for every edge vi comma vj of G I less than j. That means we'll take some example. A to B and some C here and some D here. Now these are the vertices v1 comma v2 to up to vn. So what are the vertices? The vertices are a comma b comma c comma d, such that for every edge, what are edges we have? A to b is one edge and a to c is the other edge. So for every edge of vi comma vj for particular graph, that I and j relation should be I less than j. That means increasing order. So when you are at A vertices, what are edges from A available? A to B and A to C. In as far as topological ordering is concerned, we have to first of all visit A to B, because there are two edges which are A to B, A to C. So B is lesser than the C in topological ordering, alphabetical ordering. Now B is smaller, right, than C. Now the edge A to B will visited first. That means we will take some stack and whichever is having no visiting of the vertices, that we will push into the stack. Now B is not having any edge, correct? So there is no out edge from B. So B is not having any edge. Now we'll push into the stack. But you cannot push A, because stack is meant for to keep the vertices which are not having any vertices to visit. Now A is having a vertices to visit C, so you cannot push A. Now, so B doesn't have any visited vertices, so I'm just pushing into the stack. Now, after you completed this, now again we'll come to A to find it out any other vertices. Now from A to C is there? No, there is no. Let's suppose that A to D is one edge. So comparative to C, comparative to A to C, A to D, A to C has to get visited first in the relation of I less than j. So C doesn't have any edge to get visited, so we'll push into the C. Now A to D, then we'll push into D and then we'll push A into the stack. So this is the way how topological ordering is maintained. Now we'll take some example and we'll find out the topological ordering for a particular graph. Now this is the example. So what we will be going to do is, we'll begin vertex from G. Now this is the starting vertex. Now let's find out what are unvisited vertices from G. Unvisited vertices are from G, you can see G to A and G to B, correct? Once you finalizes which is having the topological ordering, that means I less than j ordering. So in that sense, in this sense, you have to visit A first of all. That means we are at A. Now after this you will be visiting even the next is what? After you visited A, then we will be finding out any vertices which are from A. Now we will consider A. First of all I am considering G. Then I'll be considering A. I am not pushing any element into the stack. The reason why I told you in the before slide, that means when you visit A vertices, A is having the other vertices in connection with the edge. So you cannot push A. You cannot push even G, because G is having the other connection with B. Now, so after you find A, that means considered A now in alphabetical order. Look for its unvisited neighbors. Now A is having F and B. Now I'm just visiting this B. Okay, so what are visited? G is visited and A, B are visited. Once after I finish with B, there are unvisited vertices of A still. That means F. A, B, F. So where we are now at F vertices we are. So F doesn't have any other vertices to get visited. Now visit F, look for unvisited neighbors. Since F has no unvisited neighbors, push F into stack and move back to node A. A has B and B has unvisited neighbors. So stack is meant for what? Whichever vertices having no visiting vertices, that vertex has to get updated into the stack, push into the stack. Now we will be visiting B. In the second step, this is what first step. Second step is what? Visiting B. It has H and it has G. G already finished, right? I mean G it doesn't have, it is the direction from G to B. So from B you have only H. So do you have any vertices from H to reach? No. There is no out edge from H. So push H to the stack. Now and again move back to B. Now B also has no unvisited neighbors left. So push B into the stack. Move back to A. A has no unvisited neighbors. Push A into the stack. And move back to G. G has unvisited vertices, which is C. Since it has no neighbors, push C into the stack and move back to G. No unvisited neighbors, push G into the stack. Now your stack is consisting of what? F, H, B, A, C, G. And still to go, there are other vertices which we are not visited. Now consider another vertices which is D, which are we visited, that you just mark with double circle for the clarity purpose, that's it. Now so we'll go to D. Consider another edge, another vertex D. Visit D, move to its unvisited neighbor which is E. Now E is having unvisited neighbor which is I. E is having only one, which is I. So before you comes to E, you have a conflict, right? That D to E is there, D to I is there. So topological ordering is what? Whichever is having lesser number, that means E will come before I. So that's what we were gone for, D to E, not for I. So when you are at E, you have to think that what are the unvisited vertices from E. So I is the unvisited vertices from E. Now I you have to visit. Since I has no unvisited neighbors, push I into the stack. Then, so again move back to the vertex E. E has no unvisited neighbor, then push into the stack E and move back to D. Also, D also has no unvisited neighbors, push D into the stack. Now your stack is consisting of what? D, E, I, G, C, A, B, H, F. That means we visited all the vertices except of this J. Now choose vertex J, visit J. Since all its neighbors are already visited, push J into the stack. Now, since all the vertices of the digraph are visited, pop out the stack, and popping order of the stack is what? That is of your topological ordering. So topological ordering is what? J, D, E, I, G, C, A, B, H, F. This is what topological ordering. Now we'll see the complexity of this topological ordering. Let G be a directed graph or a digraph with n vertices and m edges. The topological sorting algorithm runs in big O of n plus m time using big O of n auxiliary spaces and either computes a topological ordering of G dash or fails to number some vertices, which indicates that G has a directed cycle. So the time complexity of topological ordering is what? Big O of n plus m. Right? Now, so this is about topological ordering. What is topological ordering? The definition and the example problem, solution and the time complexity of the same. Thank you all.